Good morning. So I'm like half playing this game at the moment, but also, I actually haven't played it in years. But I also just wanted to show you a lot of like what's going on in the lighting in something like this, and you get to see a lot of things. My little robot is shooting things, but look at my little robot and how shiny it's it up. There's a lot of effects going on here that aren't necessarily things that I've taught you. But you can see, like, some of the simple things, like just the diffuse lighting. Some of these areas that, like, you know, some sections here are brighter than others. And then just the sort of obvious, I'm pointing at my screen here, but like the obvious reflectivity off my character. I'm playing on a level here where I'm much higher level than the enemy, so I can just take these hits and I'll probably won't hurt. But yeah, if you look at the way that the light reflects off the surface of the character, some of that is what we call specular highlights. The material is made to look like it's shinier than it is, and it does this by reflecting the idea of a light source off it. This is Warframe by the way. It's a pretty impressive free-to-play game because it's been like, oh wait, target for the mission. Not disturbing at all what you do to capture a target.
We'll interrogate the captive back at base. Your part is done.
I didn't think I was actually going to finish this mission. I thought I was just going to show it. Make a run for the exit. Bicycle. So the interesting thing is once you've learnt a bit of graphics, you see this kind of like, you see more in games than you've seen before. So I can just look at this box here and just go, oh look. As I was getting shot, we would see the reflection of the light in it, and we can actually see this green light being reflected in it, which I think is one of the lights coming off me. Let's get to the exit. I just wanted to, I suppose I could just abort the mission to get to the exit, but I'm not that far away from it now. I wanted to show you inside the ship as well, because there's a bunch of stuff there. Maybe I should have picked one of these ones that moves faster. This one's quite a defensive. The Warframes, they're called. The kind of the suit that you wear. This game has really nice animation as well. Like, you can see the kind of skinned animation happening as they go into these slides and stuff. And it's really funny because, like, up until this point, we may have just sort of accepted what was going on in games that we're playing, but the more you learn about it, the more you can start to think about what actual tech actually sort of went into this and how it works. Someone was saying they remembered me saying I had like 5,000 hours. I think it's 500 hours rather than 5,000, but it's still probably more hours than should necessarily have gone into like one game. Okay, so now that we're in here, we can see the close-up, and you can just see, oh, look at that little disc on the head of my character there. See the way that reflects the light? So there must be a light source above me. There isn't even definitely a light source above me, but there's at least a virtual idea of a light source. And look at the I love how I'm pointing at it. Look at the light reflecting off the floor there, and look how the floor is transparent in this area, semi-transparent. So there's so much stuff going on now that you have a decent idea about how this is all created. So I might like let this go now, and we'll go to the actual slides. So someone's asking what Warframe that is. That's a Warframe called Frost. The game is called Warframe, and it's remarkably good looking graphics. It looked like this quite a long time ago, and there's more stuff going on in that game than the techniques I've taught you. So I'm pretty sure that a lot of what's going on there is this thing called physically based rendering, where we have a great deal of detail in the surface materials of objects. So I've taught you a tiny bit about surface materials, but this is actually going a lot deeper into surface materials. Yeah, someone said Frost. Yeah, that's Frost with a weird head, because I've got helmet add-ons for the Warframes that actually change your stats in the game, which is a very old thing that they removed from the game at some point, but if you had them, you got to keep them. Because I played the game before it was released, so it was like a very long time ago. Someone's saying Control Shift Space is the only thing you ever did. Yeah, where you slide and then jump and stuff. It's got quite a fun sort of parkour thing to just make movement not a static thing that's happening. So you've got your crouch, your slide, your jump, slide, and all this kind of fun stuff. Yeah, and Jason's saying there particles and lighting. There's so much going on in that game. And it was interesting how much that game had very early on, when other games were still, other games still had visible polygons at the time, and this one has all this really smooth kind of motion and animation in its characters. So I think there's a lot of amazing stuff going on, especially for a game that initially was I think was always free to play. And it's one of those games that's managed to be a game that's been free the entire time it's been in existence, and it's been in existence for, I want to say, like nearly a decade or something now, and has managed to somehow be a free game that has never quite angered its its fan base and its following. So it's interesting. Kumara's asking what my inner guy looks like, but I've already left now, so I didn't actually go over and look at it. I just wanted to show you just how good the lighting is in a game like that. And it's a lot of the combinations of stuff I'm talking about, as well as effects and things added on top of what we've been learning about so far. So we're still going to learn more. There's still more stuff to do today. So last lecture, we started looking at lighting. So it was a lot of thinking about, like, what is light? What is the difference between the way that light works in the real world and how we're going to do a simulation of light, how we're going to make things look similar to what happens in the real world, but also not necessarily being able to be as accurate as what's happening with, we're talking about billions of photons and us not being able to kind of simulate quite that many things. So instead, we've got this Phong Lighting process. And so what we're going to do is finish looking at the details of Phong Lighting. So I've presented ambient and diffuse lighting, but we haven't really talked through all of the mechanics of diffuse lighting and how we might implement it. You are going to get a chance to do that in tutorials this week. But I'm going to keep going, excuse me, looking at diffuse, and then also stepping through specular and how that works. And so that's what we're going to do today, is we're going to do diffuse and specular, and we're going to look at dealing with multiple lights. Not just multiple lights, we're going to have a quick look at multiple light types. So there's things you'll be able to do with the different types of lights, and the fact that with different types of lights, you're actually going to have to write different shader code to deal with them. So there's a bunch of processes that we're going to go through and discuss how we would do that. I'm not necessarily going to get into code. there's never quite enough time for that. So that's why we've got this kind of split where, excuse me, weird throat this morning. One second. Sorry, just had to shut the door. My partner is in the middle of conversations and things, and when I can hear her in the background, it distracts me and I can't tell exactly what I'm going to say. All right, so anyway, so we're going to deal with multiple lights, the different types of lights, as well as what we do when we actually have to render more than one light at a time. Because most of the stuff I've spoken to you about so far is just a single light. Commercial saying I'd argue that Warframe is a bit too blinding of a light show at times. Yeah, Warframe is like full of effects, so it's kind of cool. Like sometimes it's you can see that like it's interesting, but at other times it's like the graphics programmers have been let loose. And Commercial's asking what kind of lighting did Warframe use? Ray tracing, ambient, diffuse lighting. So there's no ray tracing in it, as far as I know, unless things have changed since the advent of the current era that involves the sort of RTX series of graphics cards being able to do ray tracing. I haven't seen any evidence necessarily of ray tracing there, but it's hard to tell if there is or there isn't. I should have had this discussion while I was still in the game, because there are reflections happening, and they look like direct reflections, but they also look like they could just be the standard code that we'd run for reflections of flat surfaces. We're actually going to talk about that in the course, because one of the things I want to do is things like reflecting surfaces and stuff like that, because that's quite interesting and introduces a new way of thinking about things that we haven't covered yet. Anyway, we'll get there when we get there. I might even bring Warframe back when we do that, but then who knows? There's going to be plenty of games that have reflections in them, like mirrors or very, very shiny surfaces that aren't just shiny like I was showing there, that just have reflections of light off them, but might actually have reflections of images off them. So could be cool. Yeah. Nix just woke up. I remember, Nix, you were saying you're in another country, so this could be very early in the morning for you. Okay, so continuing what we were doing with diffuse lighting, let's have a look at an example. I've got a reasonably simple example here where we're ignoring what's happening in the z-axis, so we're just using it as if we're just like a flat cut on the z-axis, where the z coordinate on each of these positions happens to be 0. So most of our vectors are going to be two-dimensional vectors, so they're just going to be on the XY plane. And so we've got this green box here. We've got the camera looking at a particular fragment on the green box, and we've got our light source in a particular position. So looking at the numbers here, we've got a light at 450, which is its position in the world, and the colors on the light are 0.8, 0.8, and 0.5. So I'm using a particular scale of colors, which is between 0 and 1.0. So full intensity at 1, no intensity at 0. There are other ways of doing this. When you have something like 8-bit colors, or you've got 32-bit colors that you're using, you might actually have 8 bits per color, so it could be 0 to 255. But a lot of the time we're going to be using floating point numbers for these. And so I've just done them as floating point numbers here. And the ambient light that we have is 0.1, 0.1, 0.1. So it's very, very dim, but only like sort of 10%. Kumaresh is asking whether reflections also means shadows. Unfortunately, no. Shadows are very interesting, and we will talk about shadows as well. I don't know how much depth I'm going to go into shadows, whether we'll actually implement them or not. I'm just kind of seeing how much we can squeeze into the remaining weeks of the course, in a sense. Like, I need basic lighting. I think that's very important. And I want to do reflections because they're really cool, but some of the techniques that we use for reflections can be applied to creating shadows, but we'll get into that. Okay, so I've got my ambient lighting's fairly dim. So remember the difference between ambient and diffuse lighting. Diffuse lighting is direct light from a light source that hits an object, and it's going to be bright depending on whether the object is facing the light source or not. Whereas the ambient light is meant to be light that has already hit multiple objects in the scene and has just bounced around. And we were doing a very, very simple implementation of ambient light where we're saying that it's just all through the scene. You know, we're not too worried about how many bounces it's been through or what color it's picked up on those bounces or anything like that. It's just static light through the scene. The fragment we're currently rendering, so it would take us a while in the fragment shader to go through, say, here to here, every pixel, in a sense, that the camera can see. And so we've picked one of them to do this calculation because, like, you know, if we're going to do this by hand as humans, it's going to take us a lot longer than how long it would actually take to render all of the fragments. Each of these fragments is like, you know, I'm thinking a millionth of a frame to do it because we're capable of like rendering a lot of fragments. Especially in a scene as simple as this, there would be a lot of fragments we could run at on a modern graphics card. So we know where a current fragment is, and I've just made this easy for us. I've put simple numbers in. It's not even that simple. There's going to be like square roots and stuff turning up in what we're doing, but you know, it's reasonably simple. The surface normal is pointing straight upwards, again, just to make our calculations a little bit easier. This is the flat top of a rectangle here, but it could be the top of a cube or something like that. And so its surface normal is pointing straight upwards. This also makes it a little easier for us to see what's happening with the calculations if we were to change them. I haven't done all of the calculations for us, and I wasn't sure whether I was going to do them all by hand or not. I'm going to keep an eye on the clock and see whether we're going to do that. But the reflective color of the object is mostly green, so there's a bit of red and a bit of blue. So it's like on the teal side of green, but it's still green. Because the dominating color here is the green out of the RGB. I didn't get too tricky with it. Mixing colors too much, but if you look at the colors, you've kind of got red, green, and blue, and then in between red, green, and blue, you've got the cyan, magenta, yellow, if you've heard of those. And there's actually two different ways that we think about creating color, is that when we are emitting color from a dark surface, which is like our computer monitors, they start off black, but the more light you put into them, the more color you get. Those colors are red, green, or blue. But there's another way of doing colors, which I don't know if I've talked about this before, actually, which is the removal of color. So you start with a white surface, and the more color you put on it, the darker it gets. And this is what our printers do, because our printers use ink to darken the white paper. And those colors are cyan, magenta, and yellow. And it's like 6 colors in a circle where red and green go together to make yellow, green and blue go together to make cyan, and then blue and red go together to make magenta. And so if you've got any set of those 3, you can make the other sets of them just by mixing the colors. So you can look into that if you want to. It's sort of interesting. There's lots of stuff on color theory that we haven't really gone into too much in this course because we've been working more with the technicality of coding the graphics rather than necessarily how a printer might work as well. Okay, so this is the data that we have behind the information that we're going to need to do our lighting here. And then we need to look at this equation. So this is part of the Phong lighting equation. So what I've got is the intensity of the ambient light, not necessarily the intensity of the light, but the intensity of the ambient reflection from that fragment, and the intensity of the diffuse reflection from that fragment. And so the ambient is actually this first bit here, and the ambient's the simple one that we've looked at before, which is like the ambient intensity of the light versus the ambient reflectivity of the of the source object. And then here, this part here is the diffuse part, where we have the diffuse reflectivity of the object multiplied by the diffuse light coming from the light source, and then that is moderated by this dot product, where n is the surface normal here, 0, 1, 0, as we said before, and L is something that needs to be calculated still, which is a vector aiming at the light from the fragment. So, looks pretty complicated here, the way we've done this, because this is like, you know, the formal mathematical representation of this. But what we're getting is, if we break these down into parts, it gets much simpler. So the ambient is really simple. It's just a multiplication. And so I've put some numbers in here for things. So the ambient intensity, as I said, was 0.1 in all colors. The ambient reflection, we're using the same color. So we're assuming that the object is a simple object that only has the same color for ambient and diffuse lighting. You can get objects that have different colors from different reflectivity. So you'll note in what I was showing you at the beginning, my character had this little disc on the top of their head, and it was blue, but then when the light reflected off it, it was white. So it's one of its reflectivity colors was pure white, but one of its other reflectivity colors was that dark blue color. So I think that's interesting, because with the ambient reflectivity, the diffuse reflectivity, and then the specular reflectivity, which I'm going to talk about later today, changing them in different ways can make an object appear to be a different substance. And so when you start to learn about how different substances react to light, we can actually change these settings so that we've actually got a lot of flexibility in changing the surface material settings, in a sense, to get it to appear differently. Okay, so our ambient and diffuse reflectivity on this object happen to be the same color, just because it's going to make our calculations a bit easier here. The L is a vector to the light source. This needs to be calculated. We haven't done this yet. Our surface normal, 0, 1, 0, and our the intensity of our light, the actual light source, is this largely yellow color, 0.8 in red and green, and 0.5 in blue. So it's on the yellowish side. Actually, it's not, I don't know whether that would necessarily be yellow, but it'll be close to it. I think to get pure yellow, the blue component would have to be a lot lower than this. So this might be a little bit of a pale tan kind of color. I don't know if I could call a light source tan colored, but it's yellowish light source. Yeah. So we actually have most of the numbers here to just punch these into the equation. The one thing that's missing is the L, and we do want to look at the L.N to have an idea about how this is working. So I've now drawn the L vector in here. So it starts at the location of the fragment, and it ends at the location of the light source. That is going to be the direct vector, in a sense, between those two objects. But what we're going to want is an actual direction vector to that. And there's a subtle difference, but very important, but subtle difference between those two, in that one of those is a vector that can traverse our scene, in a sense. So it has quite a long distance to it. But if we want to do lighting calculations with directions, we want to make sure that these directions are shown to us in a very specific way, in that they all need to be length 1, because if they're not length 1, we're going to multiply them by things and they're going to cause problems. Even just a dot product of two vectors, if they're not the same length, the dot product will be kind of skewed, in a sense. And if they're not length 1, then the result of the dot product won't necessarily be this ratio of 0 to 1 that we're going to use the dot product for. I've got more slides to talk about that. All right. So the direction of the vector, we have the start and the end of the vector, and it's actually quite easy to find a direction vector, because what you do is you take the end of the vector and then you minus the start of the vector. And that will give you a vector between 2 points. So anywhere in any scene with coordinate geometry, we can draw vectors between locations of objects just by minusing the end from the start. So here we have the endpoint, which is the light, which is 450, minus the start point of the vector, the fragment, which is 120. So 450 minus 120 is going to get us 330. I've put normalize here because the actual sort of mathematical notation of it takes a little while to write here, and so it's fiddly. I don't really have all the fonts, mathematical fonts, in this slide layout to do it. But what we do to normalize is to divide a vector by its own length. So what we need to do first is find out the length of the vector and divide each of the components of the vector by the length in order to create a unit vector, which is a one length vector. So let me just hop into good old Microsoft Paint here. This should be reasonably familiar to everyone, the idea of Pythagorean triangles. So a squared plus b squared equals c squared. This works in right-angled triangles. It doesn't work in other triangles, but specifically right-angled triangles. The beauty of that being that anything in an XY coordinate space is already a right-angled triangle. So if I just copy my vector, so what was it? 120 and 450. What I would use for that is so 4 minus 1, 5 minus 2, they're both 3. So my vector, what color was it? It's one of these. My vector here is 3, 3, 0. I've actually already created a right angle triangle out of this. So let's use these colors here, do that and that. You could even consider these to be two separate vectors. This is length 3. This is length 3. Obviously my drawing's not perfectly to scale. It wasn't a perfect 45-degree angle. But we can now figure out that the length of this this hypotenuse of the right angle triangle has to be 3 squared plus 3 squared equals hypotenuse squared. So 3 squared is 9. Add 2 9s together. This thing is the square root of 18. If you remember your mathematics with square roots and stuff like this, we can actually reduce this down a little. So what we're going to get is our final vector. So let's draw this in another color. Our one length vector, unit vector, is going to be 3 on root 18, 3 on root 18, 0. So as I was saying, like when we work with square roots, we can pull some square roots out of this. So root 18 is actually equal to, we pull a 9 out of that and square root the 9. So it's actually 3 by root 2. Which makes this all quite convenient. You know, I kind of doctored the numbers, so this would be reasonably convenient. So if we divide 3 by 3 on root 2, each of these sides is actually 1 on root 2. And this is 1 on root 2. So our final vector then, I think I put the numbers. Did I put the numbers? I didn't put the numbers in. That's all right. I actually didn't put the final numbers on a lot of these things in just because it's like, it's going to be fiddly to calculate them. Especially because now that I've got 1 on root 2, I've got a lot of decimal places and I didn't bother writing all of them in on the slides here. But either way, wait, was Warframe still running? No, it's not. Okay, good. That was just my Steam window in the background. Okay, so my final vector then here ends up being 1 on root 2, 1 on root 2, 0. And if we put this back into one of these triangles, we could actually find out pretty easily that if we square both of these, add them together, and then square root them, it's going to be length 1. So we can kind of, in a sense, check these and guarantee that our normalization process, dividing the vector by its own length, ends up with a length 1 vector. We won't always have to do this. As I've told you before, OpenGL has a lot of maths math stuff for us. So GLM, which is the maths library, going alongside OpenGL, just has a function called normalize, which means that this text that I wrote here is actually closer to the truth. We won't be doing the square roots and the calculations and everything like that in OpenGL. We'll just get OpenGL to do it. It's nice to know, though. It's nice to remember how to do this maths, because it's the basis of what we're doing. Okay. Let's look again then at the dot product. Now, I've spoken about dot products before and what they're going to do, but it's good to just kind of remember that, and then also look at this kind of image that helps you remember how this works. Cos of an angle is a wave that's going to go up and down like this. So the cosine starts at 1, and then it drops to 0, goes down to -1, comes back to 0, like that. If we take two length 1 vectors, two unit vectors, we're going to get a cos on a 1 to -1. If you take different length vectors, this is not limited to 1 and -1, but we like it to be limited to 1 and -1, because what we're going to get out of that is we're kind of going to get a percentage, in a sense. So what we're going to get is, this is the angle between two vectors. So if I convert, this is in radians, if I convert these to degrees, this is 90 degrees here. So each one of these is 90 degrees, and here we are at 360 degrees, which takes us back to this 1. So what we're actually saying is, when the two vectors have no angle between them, so 0 degrees here, 0 radians, if we have no angle between them, we get a value of 1. So this thing is telling us that if both of these vectors are aimed in exactly the same direction, we get a full value, which is kind of good, because it says if the surface normal of the object is aimed directly at the light source, then we get the maximum amount of light. And this gradually drops off right until the light is going directly across the surface. And if it's going across the surface, we don't expect any light to hit the surface. And especially this whole section here, when the light is behind the surface and can't hit the surface at all, it's going to be below 0. We're never going to use below 0 in lighting. So what we're going to do is basically have our cos wave look a little bit like this in our implementation. So basically, once there's 0 light, we're going to just clamp it at 0, so that it doesn't actually do the bit of the cosine wave that would go below 0. If there's no light, there's no light. There's not necessarily negative light. You can use negative light to do some cool stuff, but not necessarily doing that. Jason's asking, how does NVIDIA make these things just work? Do they have to implement some kind of hardware light accelerator? It's not necessarily just working, in a sense, that it's just that someone else has written the code. The only reason that, like, say, normalize happens in the library is because someone else has written the normalized code, which is not that much different from what we just did. Find out the length of the vector, divide each of the vector's components by the total length of the vector, you'll end up with a 1 length vector. It's just that we don't necessarily want to manually rewrite that code every time. Although, maybe I think you're asking about how they just work. You know, NVIDIA has this hype marketing thing. They just go, like, ambient occlusion just works. Real-time reflections just works. It's like, I think it's the NVIDIA CEO or something just likes to say the phrase just works all the time. And I think what they're referring to is how many things that how many techniques have specific it's not even just hardware, it's hardware and drivers help for it. So things that will be like, we could punch in something like Phong Lighting into an NVIDIA card and it identifies it and says, yeah, I've got specialized hardware to pick up those particular things and make them work. That's what ray tracing is. Like there's specific hardware and driver setups in the RTX line of cards that says, oh, I know this ray tracing thing. We have hardware optimized pathways on the graphics card. Well, not pathways, but like sequences of processing in a sense on the graphics card that's going to do this in the fastest way possible. I think that's what they mean by just works, because nothing just works. Everything works on the back of a great deal of effort and like low level programming to make sure it's the most optimal it can be. But I think for all those of us who are at a higher level of programming, like actually writing shaders and stuff like that, the just works bit is hoping that the hardware is going to do this in the most efficient way possible. Yeah. Okay. So the dot product is going to give us a ratio of the angle between the things. So if the surface normal is similar to the angle to the light source, we should get a brighter bit of lighting there. So the equation here is going to be the ambience plus the diffuse components of the Phong lighting. And the ambient one here is pretty simple. We're going to take the ambient light intensity and multiply that by the reflectivity of the surface. So the surface is mostly green. The ambient light was quite dim. I didn't actually bother punching the numbers here, especially because once we get into these, the numbers are going to get pretty complicated. Although it's not too bad here because the vector to the light and the surface normal will multiply out with the dot product here to just be 1 on root 2. So we would get the factor of how close this vector is to this vector in their angle is 1 on root 2. And I did set that up on purpose in that this vector to the light is exactly 45 degrees and this vector is straight up. So the 1 on root 2 is like a kind of a known quantity at 45 degrees here. So what we're getting is, because the light source is not exactly the light source is not exactly aligned with the surface, not all of the light from this light source is considered to be hitting that surface dead on and at full brightness. So what we're going to get is the diffuse component at that fragment is going to be the reflectivity of the object multiplied by the intensity of the light source, and then moderated in a sense by the angle of the light. And if you want to, like, we could actually crunch the numbers and bring this out, like, but I haven't done it because once I start doing it with a 1 on root 2, I should probably just throw in a bunch of decimal places, and then there's going to be an arbitrary number here. But you can try this out yourself. But the thing that you want to do if you're going to try this out and actually multiply out all these numbers by hand is try moving this light. So what you'll find is we'll get a certain number here with the light at 45 degrees. If all I do is just change the x coordinate of this light, if I lower the x coordinate so it's closer to this 1, so the light becomes more vertical, like directly above the normal, you should see the intensity of the diffuse component will go up. If I pull it further away, the intensity of the diffuse component will drop. Another cool thing is if I take the light and I bring it below the level, below y equals 2, what I should get there is the diffuse component will turn it into 0 and then actually turn into a negative number. At the point at which it turns into a negative number, we would ignore it. Because the cos graph would drop below the x-axis here, and then we do this kind of thing where we go, okay, clamp these things at 0. If it's negative, we're just going to ignore that component of the lighting. Stardust is asking, if you reverse these dots, will it look transparent? It won't necessarily look transparent, right? Because this isn't going to allow us to see through things if we have negative lighting. The weird thing is that what it's going to do is it's going to artificially darken the component if it's negative. So whatever ambient light, so the ambient light's not based on direction, it has an amount of light. If this was negative, it would actually remove the ambient light from something just because the light's not aimed at it, which is not really what we want to have happening. It can't make something transparent because the object will end up being like a solid black, because transparency involves the order of rendering, and then you'd have to render using blending. So that's something I was talking about in, I don't know which lecture. I was going to say lecture 7 or 8 or something. I can't remember. We're on to lecture 12 now. I don't remember the lecture numbers, but if you go back, there will be a section on blending, which actually talks about transparency. So that's what we need to do for transparency, because in order to have transparency, we need to be able to render the objects behind and then the objects in front and blend the two colors together. This lighting equation is only dealing on a per fragment basis. So we would render the back object and then we'd render the front object. And then after we've done the lighting on those two objects, we would then take those colors and blend them together for transparency. So the lighting equation itself can't actually help us with transparency, sadly. Okay, so that's the details of how we would actually do the maths to render this particular fragment here. So talking about how this happens in the shaders, I'm not going to talk about this too much because you're going to do this in your tutorials this week. You're practically actually going to be writing the shaders. But let's look a little bit about what might be happening. So our vertex shaders are going to give us a certain amount of information. So they're going to give us our fragment position. We didn't always need to use the world coordinates of our fragment position, but here we can. I mean, this isn't always done in world coordinates. Like if we're in a fragment shader, we might actually be doing this in view coordinates as well. Remember how the view projection matrix. Wait, the model view projection transform matrix. I was like, I know there's a lot of words here. I just got to get them in the right order. Turns everything into the viewpoint of the camera, so the camera ends up at 0 and all the objects are relative to it. You can calculate this either in view space or in world space. It's the kind of the same calculations in a sense. It just depends on which coordinate space you're in. So we would have a position for the fragment. So the fragment exists in either of these coordinate spaces in certain position. We'd figured out the surface normal. So there's two ways we can figure out the surface normal. I was talking about this last lecture. We can either make it from the vertices, so we're talking about triangle winding cross products to make the surface normal, or we can take normals that are on our vertices. So our vertices might actually have surface normals there, and we'd linearly interpolate between those surface normals to figure out what our normal is. This is the same way that we linearly interpolate between texture coordinates, or we linear interpolate between colors that are put on each vertex. So we can do either one of these things depending on how your system's going to work to figure out the surface normal at the fragment. And then, as I was saying, linear interpolating color or texture coordinates, something the vertex shader will pass these things through to the fragment shader. Fragment shader will take in those outputs from the vert shader, but also we'll need to know what position or what direction the light is. So some lights don't have a position, they just have a direction that they move through the scene in a sense, and that will be a vector. Or we have the light position and we'd find out the direction to the light by minusing the light position from the fragment position. So that's why we need the fragment position getting passed through, and the light position being what we call a uniform in the shaders. The keyword uniform, it's like a variable that says that no matter which fragment you're currently working on in the scene, this is the same value for all these fragments. So we know that we can run the fragment shader several thousand times to do all of the pixels on our screen, or actually more than that, probably millions of times to do every pixel on our screen, but the position of the light source in the scene never changes in the rendering of a single frame. So those uniforms are actually a little easier on our memory because we don't need to generate them each time. Whereas obviously the position of each fragment changes because each pixel is looking at a different place in the scene. So this has to be recalculated for each fragment. Whereas the light position is what we call a uniform. It just stays the same place. And the light color will be another uniform. So the fragment shader will say, okay, we've got all these stats about where we are in the world, what our surface normal is and stuff like that, what our light position or direction is, and the color. And so then the fragment shader will go and calculate the light direction. If it was a position, not a direction. If it's a direction, we just use it. But if it was a position, we would then calculate the light direction per fragment because every fragment is in a different place. So it would have a different direction to the light source. We've shown that a second ago, so I already showed the calculation of the light direction. And then it will complete this algorithm by saying, okay, I do these multiplications, I do this dot product, I do all of this, and I add these together, and I've got, for the moment, ambient and diffuse lighting. We're going to add specular to this in a second as well. Yeah, so I'm not going to go into too much detail in terms of the code, but I mean, I'm talking through it. You'll actually be working through this kind of code in your tutorials. Oh, Hamish is asking, yeah, how do you pass the lights to the frag shader? Yeah, this will be in the tutorials where we'll talk about how to actually like put the uniforms in the frag shaders and stuff like that. But it's basically that same kind of thing that we were doing with any other data that goes into our shaders. All right, so let's move on now. Specular lighting. So there's a reason why I was showing you Warframe at the beginning, because Warframe is just like really over the top with its specular. Like everything is made of metal, everything is shiny, everything has a whole lot of like, you know, those direct white blowout sections where you can't see the color of the texture anymore. All you see is this strong white reflection from the light source. And that is what specular lighting does. So I've talked a bit about what it means previously, that it's like a metallic surface or a shiny surface and things, but let's have a look at the equation itself. So the intensity at that fragment of specular light is going to be the specular reflectivity of the fragment multiplied by the specular intensity of the light source, but moderated by another dot product. It's a more complicated one this time though, because R here is the vector of the direction of reflected light, dot product with the direction of the viewer. So we are doing a similar thing here. We're taking two vectors and we're comparing how close or how far away they are. Oh, it's not really far away, whether they're aimed in the same orientation or not. And that's going to be the angle towards the eye, because what we're looking at here with those specular reflections, you saw as I was moving around the scene, the reflection just kind of moved across those objects. I kind of want to have like that scene continually running in the background while I'm talking here, but it'll be a bit noisy as well. Because the trick with the specular reflection is we're looking at not just whether the light is hitting the surface, but if the light is hitting the surface and bouncing off at exactly the right angle to like blind us with the reflection of the light source, then we want that fragment to just go white in a sense. It's not necessarily full white, but we want it to go bright so that we can see that the light source is being reflected off the shiny surface. And it gives it that really cool look where something could read as just like a dull plastic surface or something like that, but the second you see those specular reflections, it reads as like a metal or something. And so you can do some really cool stuff. And we even saw like in those examples that some of the surfaces that were reflecting light of parts of their surface, and other parts of the surface were not as reflective and things. We're going to talk about that next week, because we can actually control how much reflectivity a surface has with a material, with a kind of a texture, But we'll get into that later. We want to do the basics first, learn the formula and how it works. Okay, so this thing here is something we're going to have to calculate the reflected vector and the direction to the viewer. And then we have this A here, which is the Phong exponent. I'll explain this in a second, but it's interesting. It's just a number that changes the characteristic on things, and it may or may not have any grounding in reality. Like, it sort of does. But again, this is like one of those approximations of reality that we're just going to use. It is kind of abstract. Like, there is no Phong exponent in the real world. There is, I guess, a measure of shininess in the real world, and there's enough. It's enough of a connection that you can kind of use it. Then we have the specular intensity of the light source, which is just how bright that light's going to be and the color that light is. We'll often use the same settings for diffuse and specular from the light source, but different settings in the material, because some materials are going to be shinier than others. There's a lot of stuff we can tweak here in order to make things look different. So, for example, what we had in Warframe there was the diffuse component was blue and the specular component was white. So that gives us a really shiny surface that reflects all light directly. But in terms of the light that it just sort of scatters, that allows it to kind of be visible from any direction, that's its own color. So shiny surface that has its own innate color. So let's look at this r.v to the power of a. What is this part of the equation, how it works? So the r and v are direction vectors. So r is the direction of the reflected light. So we're going to calculate this based on the direction to the light and the surface normal. So this is actually just going to be a reflection of the vector towards the light source. So actually, I've got images. I'll show you in a second once I've talked about this. V is the direction to the viewer. So the direction from the fragment to the camera. So we're now going to need the camera position to be able to do this. So I've drawn it here. I've moved the camera because I didn't want the camera to be exactly on the 45-degree angle here. But R is going to be, see, this is L that's pointed at the light source. R is going to be a direct reflection of L. This one's too long at the moment. I'm just showing the direction. We'd have to normalize this so that it's a one length vector. And then we have V here, which is going to be the same way we calculated the L to the light source. We take the destination, the endpoint, and we minus the start point, and then we're going to get a vector here. We would then also normalize this vector so that it's a length 1 vector, because anytime we're doing lighting calculations, we need length 1 vectors. The same thing that I was saying before is that whenever you're making vectors, on instinct, normalize them. It's more of a it's more of an interesting thing when you don't normalize a vector. Nearly all the time, you're going to want to be normalizing your vectors, because when we're using vectors, generally the only thing we're using them for in graphics is going to be directions between things, not necessarily the magnitude of the distance between things. Okay, so the R, I haven't told you how we're going to calculate that yet, but the V should be quite easy to calculate because I've already shown you in the diffuse how we'd calculate that. We would take the location that it's aiming at, which is the camera, minus the location of the viewer, and then we would normalize it. The dot product is similar to how we did the diffuse, which is the reflected light. Is the reflected light aiming directly into the camera, or is it not aiming directly into the camera? I haven't talked about the A yet, but I will in a second. Okay, so there's the image. And then what is this Phong exponent? It's made up. It's just a number. Like, literally, it is. But the cool thing is, it works. So even though it is an abstract concept, it's a made-up number that sort of means shininess. Like, it sort of, but then doesn't. It focuses that reflected spot, I guess, is what I want to say. So the higher your Phong exponent is, the smaller that white dot is going to be on the on the metallic or the reflective surface. The smaller your Phong exponent is, down to it not being an exponent at all, if you have a Phong exponent of 1, the more it acts similar to the diffuse lighting. And the diffuse lighting kind of just spreads the light across the object, and there's a tiny difference. I wonder if... Let me just see if I had... Yeah, okay. So I had this image of the diffuse lighting here. I could have opened Learn OpenGL as well. And it's actually brighter here than it is here. But you don't really read this as a super reflective surface because it's just this kind of nice smooth gradient between the two. When we're doing specular lighting, we don't want that smooth gradient, actually. We don't really want a nice smooth gradient. What we want is to get a point that looks like it's actually reflecting a light source. So this Phong exponent is going to shrink that white spot. So because the dot product of two unit vectors is going to be between 0 and 1. I mean, it's going to have negative as well, but we're not going to use it when it's negative. It's going to be between 0 and 1 for us. Any positive power of 0 and 1, so I'm just remembering the positive here, will kind of narrow its curve. And so I drew some pictures of this here, as well as Learn OpenGL showing what happens at different Phong exponents. So if we just square the number that we get, so this is the curve of r dot v. So 1 down to 0 at pi on 2, which is 90 degrees. If I've just cubed it there, I mean, like, I didn't plot these, I just guessed at the graph. So if we start raising the Phong exponent, what that's going to do is going to start dropping off this curve quicker, and it's going to hit 0 or close to 0 much sooner. So this is here where we see that, like, the intensity of the bright spot is full in the middle, and then it drops off before it reaches the end of the object. And then up here at 32, we can see that the specular lighting is probably having nearly no effect on these areas here, but it's bright here. And so this is here, r dot v to the power of 30 is going to drop off quickly, and then just sort of flatten out to have no effect. And you can see here that once the exponent gets really, really high, so an exponent of 256, we're going to get this one little tiny bright spot here where only some of the fragments on this cube are being affected at all, and the others aren't. So this is giving the idea that this object is a flat piece of, like, metal or something like that, and we can see the reflection of the light in it. This is quite subtle effect here in what we're doing with Learn OpenGL with the basics, but as you saw in Warframe, you can dial this thing up. So you can really dial this thing up to be like a hot white dot there, in a sense, that in a sense overrides the other colors in the scene. So it maxes out the color value. Because if you notice in Phong Lighting, there's nothing that stops these numbers from getting really high. So these numbers could get above 1. Your graphics card's still just going to be like, look, these are 1. Like, I can't add more light than that to the scene. And so it can just max them out fully at white. So we can get our specular component to basically overflow our colors. We've got to be careful with that and make sure that those are being used correctly. But if they're going to be clamped at maximum, we can kind of overflow our lighting to maximum and get our specular thing to just override the diffuse and ambient colors and push it all the way to white. Okay, so the Phong exponent is the thing that's changing between these different possible curves for how far away from the direct reflection into the eye is this reflection going to be visible. So this one, we've got many angles aimed at the eye, that are aimed near the eye, not even at the eye, that are visible. But this one here is saying, all right, the reflection's only going to be visible if it's nearly directly reflecting into the camera. So we get this, and then we can work with the Phong exponent. Different Phong exponents are going to give your shiny surfaces in your scene a different treatment. In a sense, it's hard to it's hard to put it in any more detail than that because the Phong exponent is an abstract concept, but it does give us the idea of shiny objects like this. All right, it's 11 now. So we'll go on a break in a second. But yeah, I was wanting to talk. I've got the scene here. This is the thumbnail. I put chicken in here as well. It's actually quite funny because here you can see a reflection. This is a direct reflection off that. So that's not actually ray traced, that reflection. I think I had a look at it and I was playing around with it because it's hard. Unless you talk to the developers, you can't necessarily know exactly what techniques they use. But I'm pretty sure it's not a ray trace reflection. It's something we call a planar reflection, where we take a surface and we calculate the reflections, assuming that that surface is flat. It works pretty well for like water and stuff like that. And this one looks like they've done it where it's flat, and there's no reflections off any of the other shiny objects, right? Because it's costly to do reflections on curved surfaces. I'll tell you about that later, though. So the bright spot acts like a reflection of the light source. So here you can see one of the bright spots there. You can definitely see a lower Phong exponent bright source off this surface. So the lower Phong exponents make things look like brushed metal, you know, like a brushed aluminium kind of thing. The higher Phong exponents will make, like what was on this, make something look like it's purely reflective, like it's super shiny. So a brushed metal versus a shiny metal are going to reflect, like a chrome is going to reflect differently from a brushed aluminium. And that's what different Phong exponents are going to give you. But the whole thing's just a trick, right? And it's a trick because when we're in the real world and light bounces directly off a surface, it's often the sun, or if not, it's still a bright light that is illuminating the room that we're in or something. And we're used to being blinded by these things. Like, not entirely blinded, but at least kind of dazzled by these. So if we just put, like, as I said here, a splodge, right? It's like, I don't know, like a splodge of white on something, or a splodge of the color of the light source on something, we're used to not being able to really pick that out. Like, you can't really, and don't try this, you can't really look at the sun and discern that it is a circle. But the sun is literally a circle, right? It's a spherical object in space. So our view of a spherical object is circular. But if you just look straight at the sun, you can't really see that. You are, like, you're already being blinded by the brightness of it. So the Phong lighting just kind of plays into that, and it's like, you know what, we're not physically accurate, we're not perfect here, but this bright spot, you're going to be used to not really being able to see detail there, so you're just going to assume that it's working. And so that's like the cool thing is again these kinds of things where we take human physiology, like the fact that our eyes can't dampen down light enough to really be able to see details when stuff's too bright, and we trick the human software and firmware in our brains, in a sense, which are made to just kind of go, hey, that's bright, don't look too closely at it, you know. And so it's nearly that like psychology of it that makes these specular highlights work. We will believe it because they're this bright spot, and also when we move our head, which we can't really compare to the monitor, but we move our camera in our scene, the bright spots will move across the objects because they're based on the reflection into our eye, whereas the diffuse lighting doesn't move across the objects, it's based on the light. However, when a light moves around things and the diffuse light changes, we'll see that as well and we'll believe it. So there's a lot of stuff in the Phong lighting algorithm which is just kind of bits and pieces. It's not exact in any way, but what it does is it gives us the right cues for us to believe in things, which I think is one of the best things about graphics. And I've said it in nearly every lecture. It's like, this is how we trick people into seeing this. This is how we trick people into this. This entire lighting equation, all of this math is just like to do a big smoke and mirrors trick to get us to believe things. Okay, it's 11:06 now. We'll come back at 11:11 and talk about more stuff about Phong lighting, specular lighting. We'll look at multiple lights as well and stuff like that. All right, back soon. I'm back. We had a question about HDR there, and I was like, yes, HDR is very cool. So HDR is what they call high dynamic range lighting. So it's where the bright spot on something like specular lighting is so bright that it should be blinding us. And so what we can do is we can actually make it appear like it's blinding us by having it affect stuff around it. I can't remember whether it's bloom or HDR or whether there's two words for the same thing. They usually go together. It's in terms of high dynamic range is like if I overflow the colors past one, we want to actually be able to do something with that. And one of those things is to just bloom it out in our vision so that it becomes brighter, larger than the object itself. It's actually happening here in this area of this image where this thing here is brightening all of the things around it here so that the whole area looks like our vision is getting blurred by being dazzled by seeing it. That's why I picked this image actually. It's like the specular here is so strong that it is doing the trick of getting us to not really look at it clearly, but the high dynamic range lighting is actually bleeding out not just in the fragments where it's calculated, it's bleeding out into the fragments around it, which is very hard to do. It's actually not fragments, this is pixels, because this will be done in screen space. So it's like after we've rendered the whole scene, we see which of the parts of the scene were too bright, and we get them to actually bleed out into other pixels. We're not going to talk about that yet, but we are going to talk about stuff like post-processing and screen space effects later. Week 9? I think. I want to do some cool reflection stuff first, and then we'll do some post-processing stuff afterwards. It's a good order, because a lot of the techniques we're going to use to do reflections are part of what we're going to use for stuff like HDR and stuff like that. So I'm gonna be like squeezing in just a few of these advanced topics by the end of term, so you'll get close to some of the cool ideas to build up a scene as complex as something like this that's in Warframe. Okay, so an actual technical walkthrough of what I've just explained previously about the specular lighting. So we've got our light source here, 450, that's our L vector. How do we get our R vector? Our V vector, I think we don't really need to work through how we get the V vector, because we've already done that with the L vector for the diffuse lighting. If I want to get a vector between two objects, it's not too hard to do. So here are our numbers. These numbers are very similar to our last example because a lot of it hasn't changed. So the light color is the same, the light position is the same, the ambient light's the same. Actually, we're not even calculating the ambient light here. It's just part of the information that's going to go into the shaders. So I probably could have removed this at this point. So we've got our fragment in the same position, same surface normal, but now we have this specular reflective component of that fragment. And so we're assuming at this point that there's a different material on that fragment. So there's one material that was the color, the diffuse color of the fragment, and there's a different material, which is the specular color of the fragment. And this specular material here is 111. So we've chosen different values for specular reflectivity than for diffuse reflectivity to show that this object is, for example, a like a glass. Oh, I don't want to do glass because we're talking about transparency, but it's a metal box, but a polished metal box that is green, but we will reflect all the light that hits it in a direct way. So it's a shiny metal box, and so we're looking for these specular components, the shininess, to be pure white, even though the color of the object is not pure white. So good example here, I guess, is there's this blue and gray metal, but there's a section there where it's reflecting. I think that is reflecting. I hope that's not just a light source that's emitting, but I think it's like it's reflecting a light that's over here somewhere. Yeah, because I think this one's also reflecting light that's over here. Yeah, so this white line there is just the hard edge of this surface, and the reflectivity, the specular component, has just kind of overridden the blue that is the color of the object and made it look white in the reflected light. So we're going to do the same thing here. Our specular component's going to be white, so it's pure reflective. You can do this in your early demos and things of it and your tutorials. I don't think we're going to get to specular in the tutorials this week. There's too much stuff to set up, but we'll be doing it next week, I think. I can't remember. I haven't looked exactly. I know the vague plan, but I haven't looked at the nitty-gritty of where the cutoff is between the two. And yeah, so this will make it really obvious, the difference between the specular reflection and the diffuse colors. So when you set them up as different colors like this, it's a little bit easier. The camera is at -430, so it's just off to the other side here. Either way, we're still going to be able to draw a vector to it. I did it so it's not exactly on the 45 degrees, so that our dot product actually has some value. Phong exponent is 20. I picked a number. That's like, I think that's one of the things that you do when you first render, like your first full Phong lighting, is you pick the exponent and you tweak it, right? So you make it really high, make it like 200 or something, drop it right down to like 5 to 10 and see the difference. I think this is worth experimenting with because it's one of those tweak numbers. Like, it literally has no meaning until you tweak it and see the difference between the different numbers. Okay, so when we're looking at the actual equation here, we see that some of these numbers we're just going to punch in from the values we were given here. Same way, we're going to pull these values into our shaders, and then we're just going to use those in a multiplication in our shaders. So we're probably going to have a function in our shader which just calculates the specular component. Or we have a function in our shader that just does the lighting of the scene. And it will add the ambient, diffuse, and specular together in one go. So specular reflection is going to be maxed out. We're going full white reflection. Multiplied by color of the light here, 0.8, 0.8, 0.5. Same as before, yellowish, bright, reasonably bright light. This section here, we're going to have to calculate some things. So in order to get the reflected vector, we're going to have to make some other vector. Well, not necessarily make. We're not always making the normal. Sometimes we're extracting the normal from our vert shader. But we're going to need a vector to the light and a surface normal in order to calculate our reflected vector. So there's just a layer of complexity above what we were doing with diffuse lighting. So I'm going to step through that particular part because that's the fiddly bit. So R needs to be calculated from where the light direction is and the surface normal that we're going to reflect it around. V, not too hard. So you can see that V and L have very, very similar ways of being created. They've just got different numbers in them because they're both starting at the fragment, but they're ending at different locations. So the V is the viewer direction, which is the vector that points at the camera. We've got our Phong exponent here, which really, this is one of the ones where we're not actually thinking about exact numbers here. We're not like we don't want to change any of these numbers. Right, we change any of these numbers, the lighting equation goes weird. Things start to look strange. Whereas our Phong exponent, we can freely shift this thing around until we find one that is the kind of right kind of shininess for how we want to do things. I think one of the only downsides to this is the Phong exponent is often just chosen in the shader, which means it's not necessarily related to the specific objects. But there's ways around that as well. We're probably not going to go too deep into this more modern form of reflective light called physically based rendering, which is definitely what's going on in Warframe. Well, not definite. I can never say for sure, but I'm pretty sure there's a whole lot of what we call PBR going on in Warframe. Yeah, okay. So this is all the information that we need to make this equation work, but let's have a look at some of the details and how the maths might come out there. Okay, so how can we calculate the reflected vector? So if we have a vector to the light and the surface normal, the formula for the reflection looks a bit like this. Now, I'm not going to go through all of the maths of the formula, but I can at least draw you some pictures of vector reflection. I'm not going to, because I'm not going to go through all of the details, but if we have, say, here's my L. Excuse me. And here's my N. And I think that there's an R. So I'll do that in a different color. R, question mark. How do I generate this R? So there's lots of fiddly stuff here. You can see there's a 2 times a dot product, and then a times by the normal again, and a minus. There's a bunch of stuff that happens here. I'm not going to go through it in full detail, but what we end up doing is we end up taking this L and flipping it kind of across the normal like this. And what we're using to make some of this work is the property of dot product, which is the projection of a vector onto another vector. So getting from here to here is actually doing a dot product between L and N, which tells us when we project a vector onto another, it's nearly like what we're going to do is, I'll draw another little one here. So if these are both unit vectors, the L is going to be lower in the y-axis than the N, because the N's going straight up. The dot product actually gives us this length. So this thing is actually L dot N. So what we do is we're actually projecting one vector onto another, which gives us how far along this vector we go. We use those kinds of dot products to actually get this reflection happening. As I said, not going to go through all of the exact maths. It's a little bit involved, but I think that you may already have learnt this if you've done linear algebra and coordinate geometry and stuff like that. It really depends on which math subjects people have done in a lead up to graphics. I'm not going to go into too much detail into it, mainly because it will take ages. And on the other hand, GL reflect. I don't think it's actually gl.reflect, but there's a function called reflect in shaders which does it for us, so we don't 100% need to know the maths, but I never really want to show you something without at least referencing the fact that there is completely logical derivable maths behind all of these things that we're doing. We're not making stuff up, we're making this up. We're making up the Phong exponent, but we're not making up the formula for reflecting a vector. It comes in many different forms. This is one particularly that uses the L that is aimed at the light. There's other formulas that flip it around the other way and do it, but either way, they're still going to change that vector from one way to the other. So if we take this formula, punch our numbers into it. So 2 times n dot L. So I already just calculated n dot L, which is easy because our n is 0, 1, 0. So if our n is 0, 1, 0, and our vector to the light, as we've seen before, was 1 on root 2, 1 on root 2, 0, dot producting these, we'd multiply this one by 0, this one by 1, that one by 0, add them all up, we get 1 on root 2. So it's actually pretty easy. The dot product is 1 on root 2. We've seen that already because our dot product from our surface normal to our light source was something that we used previously in the diffuse calculation. So we know that that thing's already 1 on root 2. And so we go 2 times the n dot L, 1 on root 2, times by the n, the surface normal, minus the vector to the light. Little bit of maths, punching this back out here, we get negative 1 on root 2, 1 on root 2, 0. And if we go back to this, so this thing was 1 on root 2, 1 on root 2, 0. This one is negative 1 on root 2, 1 on root 2, 0. So if we just look at these numbers, it's really obvious that this reflection has worked, because 1 on root 2 is how far this thing is over on the x direction. This reflected vector is exactly the same distance on the other side of this. So we know that this is going to be exactly opposite that. They're both exactly the same height off the x-axis here, which means that if this thing is an exact negative of that, it's exactly the same vector flipped across the y-axis. So this is easy for us to see because our surface normal was going up the y-axis. If I didn't have the surface normal pointing straight upwards, it'd be really hard to tell whether these numbers are working or not. But you can see there that the formula, at least in this one case, has worked, but we know that this being a mathematical formula, we know that other people have proven this. We can rely on this to reflect all of our vectors. So we know that the maths to reflect these two vectors is going to take this direction and then flip it exactly around the surface normal to be like, okay, this reflection is perfect in the opposite direction. So we know definitely that if our eye is over here and our light source is over here, we've got our reflected vector now. And now we can use that reflected vector to see whether the direct reflection from the light source is aiming at the camera or not. So punch that into our equation here. Our total specular component for this scene. It's not exactly the same scene because I moved the camera in between calculating the ambient, diffuse, and specular. But if you think about it, the camera was never involved. In fact, the camera in this example with the lighting, when I calculated the ambient and diffuse, there was no camera position. The ambient and diffuse do not care about where your camera is. They will do the same calculation no matter what. So now that I have specified the camera position in the specular, even though I drew it in a different position, if we add all of these numbers together, I didn't even write down the numbers previously because we didn't calculate them. But if we add all these numbers together for our ambient, diffuse, and our specular, we're going to get one complete illumination calculation for one fragment. I love how this takes us as humans, like with me explaining everything, it takes like an hour and a half. Also, if you count last week's lecture, so we got 3.5 hours to do one fragment. We are a little bit behind our computers in how fast this thing can be calculated. Okay, where are we? Somewhere around here. Okay, so specular reflectivity of the object. So we dialed this right up to make it like super shiny metal or something like that. And then we have our dot product here. So our reflected vector, as we calculated a second ago, negative 1 on root 2, 1 on root 2, 0 is here. Here is, I just did the numbers in the background. The vector to the camera. So you can see I got a root 26 in here. Very awkward number. But you can see the vector to the viewer is negative 4, 3, and 0 minus 1, 2, 0. This is just the basic calculation of this vector to here, but then normalized. Oh, sorry. These are the numbers before it's normalized. So what we're going to get is a negative 5, 5, 0. Oh, no, wait. 3 minus 2. Negative 5, 1, 0. So the total distance that's going to be is 5 squared, which is 25, plus 1 squared is 26. The square root of that is the length. So that's why this is on root 26 for both of these. I could have simplified that out a little bit, but I kept it there so you can just see how we're getting those numbers. So this dot product with this is going to tell us the angle between those two, how close are they aimed at each other, and then we're going to take that number and we're going to take it up to a Phong exponent, which is going to narrow the possibilities of when or where actually this has an effect. So where the viewer angle has to be in order to get the full reflection or not. And we go back here and we go, this is how it's doing it, right? So we take our reflected vector, the dot product, and then we, what's the verb for exponent? We exponentize it. We apply the exponent to it, which then narrows the possibilities at which it will have an effect on the lighting. All right, where are we? Yes, here, and we've applied the exponent. Remember, you can change this number if you want. And then we multiply that by the specular intensity of the light. For the moment, we've just said the light has the same effect in specular and diffuse, because in the real world, generally, the light just has its own color, but how much specularity an object has is based more on the object than it is based on the light source itself. Don't necessarily take this as like, you know, as a God-given truth or anything like that. You know, I'm not saying that because the real world does something, we have to do it. We can do much more interesting and cool stuff with stuff than have to copy the real world. However, if you're tricking humans, generally you want to use the things that the humans believe to get them hooked in. You only need to get them hooked in, though. After that, you can do really over-the-top, not so believable stuff. Like a person with a fan instead of a head. It's literally like a fan where their head should be, and stuff like that. You can do all these fantastical things. You can break the rules of physics and stuff like that. But if you can get people hooked enough to believe, that's all you need. And underlying all of this technical stuff we're doing, that is kind of what graphics is. Okay, so this gives us our specular intensity. Again, I'm not going to multiply all these numbers out, because I just don't want to take these things to the power of 20, and I'm not going to do it by hand. If you want to, get a calculator or plug it into like something like Warframe Alpha or something like that, you will get a numerical result out of this. The numerical result is reasonably meaningless until you see it. So sometimes it's better to take these equations, know how they work, implement them in OpenGL, and see how they work. Having said that, if you do want to actually multiply these numbers out, try moving the camera. So as I said before, if we move the camera down here, stuff should disappear. In this case, as we move the camera down, what we would get is the diffuse component would get darker, but the specular component, as we get closer to perfectly reflecting into the camera, as this thing goes down to somewhere around 3, or it's not exactly around 3 because we're not on the y-axis here, but as we move the light down to get this R, so the light will flatten and the R will flatten as well. That R will get closer to the camera. We should see the specular component of this lighting become more apparent. We could also move the camera up to get closer to where we think this R is going to be, and we'll see the specular component change. You can also do this at different Phong exponent levels, and then you will see that how close you need to get, but how close you need V and R to be to each other before this thing spikes up and gets closer to 1. Right, oh, last thing, what's actually happening in the shaders? So, the shaders are going to have similar inputs and outputs in the diffuse, to the point where most of the time we're going to calculate ambient, diffuse, and specular, or not necessarily ambient. Ambient is probably separate because it's not per light. We don't need much information at all to calculate ambient. So ambient might be calculated separately, and then the diffuse and the specular, because they have so many of the same inputs, will just be worked on together. So similar inputs to what we did with diffuse before, but in order for our fragment shader to deal with the specular reflections, we need the camera or viewer position. So the vector is often called V for viewer, so just want to remember that that is the word. But we're also referring to these things as cameras a lot. So we'll have another input, which is going to be another uniform. As I was saying before, uniform means that all fragments see the same input. Makes it a little bit easier for us in terms of the the way that we use the graphics card. Like for you, for coding, you just think of it as an input. So we have the camera position, and then the fragment shader will then do its calculations. So it will calculate the reflected direction using this kind of formula here, but in GLSL, you just call the function reflect. So as with a lot of things, I don't want you to just... I know that this is a one-liner in GLSL, but I want at least once for me to show you that there's maths involved with this that we are going to use, even if after this point, the way that we're going to treat that maths is to assume that it works and then just reuse it. A lot of computing works like this, you know. We rely on mathematicians to do a lot of work for us, you know, like even hundreds of years old maths that we use in computing. Someone spent, you know, a lifetime putting together these ideas. And us in computing, we give a lot of trust to mathematicians in a sense. We say to them, you spent, you know, the cumulative idea of thousands of years of people's lives putting together this system. All we do is, you know, we're a tiny person standing on the shoulders of giants, and what we say is like, okay, we're going to assume that your mathematics works. We're going to trust you because we understand the amount of effort that went into doing this. And then what we're going to do is turn this into a reusable thing where we don't have to re-implement the maths all the time. And that's how we end up with things like libraries. Like in the shader language, we can call the reflect function, and we get free reflected vectors out of this. So it's kind of nice like that. Yeah, Simon's saying computer science is the most fun subfield of mathematics. We get to see a lot of stuff happening a lot quicker than mathematicians do. They have to write it all out. We get our computer to do it, and then suddenly we're doing this GLSL reflect thing several million times a second, probably billions of times a second. And in doing so, we get this stuff that just moves around in real time and gets us to believe lighting. It's so cool. Okay, so the frag shader will also complete this entire Phong algorithm and calculate frag color, which adds together the ambient, diffuse, and specular. So this this ends up saying that we now have this Phong model kind of complete, and doing our learning. Bob saying, so the light source we provide has one color, or does each component have its own color? So when you're saying components, Bob's saying the diffuse, specular, and ambient. So the interesting thing is ambient light is not based on a light source. It's based on the cumulative idea of multiple light sources, maybe multiple, or even a single light source in a scene, but multiple reflected light. So ambient's actually irrespective of the light sources themselves. Then each light source may have a different diffuse and specular component. This is physically different from what we have in the real world, where the light source just has an intensity and color, and then some of that will be reflected off the surfaces, and the surface properties usually determine the specular and diffuse component. But we're in a computer. We're not doing a real simulation of light. We can do what we want. We could make the diffuse and specular components of the light different if we want to. It's hard to think of an example of why we would do that, because the real world does not have any of these examples for me to pull on right now, but you can do it because they're all just numbers in the computer. So yeah, the light can have a different amount of light for specular and for diffuse, and a different color. The objects themselves also, because they have, because what we've got an IS, which is the intensity of the light for specular, but we've got a KS, which is the reflectivity of the surface for specular. And that's much easier because I can actually draw on real world examples to show that. I can have an object that has its own diffuse color, but has a different specular color, because when it's reflective, it reflects all light. But when you're just looking at the scattered reflections off it, the color reflections in a sense, the diffuse can be a specific color. So we can see that example. Yeah. All right, cool. That's making sense. All right. So let's look at multiple lights, because not only do we have different types of lights, but we have an arbitrary number of lights. So old school limitation, we used to say that you can't have more than 10 lights in a scene. That's been broken nowadays, but in different ways and actually needed different techniques. So I'm going to talk about that though. So we've got multiple different lights. I'm going to talk about 3 kinds of lights here. Directional point lights are the ones we're going to be using the most, but spotlights are things you can use if you want to. They just take a little bit more effort. We're not necessarily going to go that deep into implementing them. I don't think, like, maybe one of the extensions. We'll see. Xavier's been writing some extensions for the tutorials in case people want to go delve deep into these kinds of things. So, directional lights and point lights. I've mentioned these before and said what they might represent, but we're going to have a quick delve into more of the maths on these today. And spotlights are something we haven't spoken about, but you will be kind of familiar with this concept because we use these in our lives. Anyone who's driven a car has used this kind of light, a light that shines only in particular directions. And we also want to look at how, if we're going to have these different types of lights, how we might actually process these lights in Phong Lighting. So directional lights, I've said this before, but it bears repeating, is a light that is so far away that it doesn't really have a position in the scene. It only has a position, in a sense, relative to the scene. So the only thing we're going to do with this is represent it by a direction vector. So this actually makes our maths more simple, because in all of the equations I've shown you the last 2 lectures, we have had a light with its position, and we've had to calculate the direction to the light. If we just get given the direction to the light, then that makes it easy. So what we're saying is, like, the sun is over there, and that's it. And from everywhere in our scene, the sun is over there. So that's the only thing that we need, is a direction vector. Everything else about this light, we just calculate the same way as we were doing. So this actually just makes it easier, the directional light. I was thinking, actually, and I think Sam, was the one asking me about this, is like actually put in the assignment that we had to have more than one directional light. And I'm thinking of changing that requirement in the assignment, just because usually in our scenes we'll have one directional light and then maybe multiple point lights. So when I said there's the criteria in the assignment for multiple lights, I said multiple directional lights and multiple point lights. I'm not sure that's the right, as I was making the lecture, I was like, oh, think about this. There's usually only one directional light in the scene. So I might change that requirement in the assignment. I'll let you know, and I'll put a change log on it if I'm going to do that. Or I could just leave it, because you could have multiple directions. Because you could have, I don't know, some kind of science fiction setting where you have more than one sun. Or you have a very, very close moon, and the sun and the moon are both illuminating something. But I don't know. When I'm trying to get you to do technical things, I don't necessarily need to have the constraints based on the real world. But most of the time, there's actually only one directional light in a 3D scene that is a replication of a real world environment. Okay, point lights. I don't really need to explain these, because we've just done our entire learning about the whole Phong Lighting thing, the whole Phong Lighting algorithm and equation, using point lights. So lights that have a location in the scene. They are usually the representation of small lights, like this one here, this little lamp, that has direct illumination on things near it. There are other things that we can do with these, because if we consider these to be small lights, if we consider these to be like lamps within a scene, you can see I brought this lamp here, and it's obviously lighting my face here. But the second I move it away, there's less light on my face. And also, this lamp is having basically no effect on the room behind me. So I can move this around. There's a little bit of HDR and bloom going on here. But it's amazing. The graphics in the real world are amazing. I can't believe how well it runs sometimes. It's having no effect on the wall behind me. And there's nothing in the Phong Lighting algorithm that I've shown you that allows this light to have no effect on the wall behind me. So what we can do is we can use a technique called attenuation. So attenuation is a very common thing with any form of radiation. It also works for like audio, which is not a form of electromagnetic radiation, but a propagation of vibrations through a substance. But to make these smaller lights more realistic, we can get them to fade off in their intensity the further away they get from objects. So you can think about this as being reasonably simple, and we've already got what we need to calculate this. Because remember what our, where's the shaders? What our inputs of the shaders are is the, oh, we don't even need the viewer position. We have the light position in the fragment. We can calculate how far away this thing is from the fragment. So all we need to do then is to say lower the intensity based on the distance. We won't always do this as like a linear thing. It's not always a straight line drop off. The way that objects that radiate in a, you know, in a spherical pattern from a light source are going to drop more like I want to think like a square root curve. So it's going to be a harsh drop off initially and then flattens out afterwards. Not going to go into the maths for that right now, but you can look it up. There's actually formulas for attenuation that can get quite complex, and you can use them quite easily because all the data is already in the fragment shader. Simon's like, that light is actually a spotlight. Yeah, it is. It is a spotlight. That's true. But look, even if the light is side on, you can still see it. So it's not exactly a spotlight, but it is kind of a spotlight. The spotlight, good segue though, is this kind of idea that it represents things like, you know, like an electric torch or a lamp with a shade on it, or headlights on a car. Anything that has like a reflector behind the light source is going to end up looking like a spotlight in our scene. A spotlight is just a modification on a point light, where what we're going to do is add an aim direction for the light. So the light has a position, a way that it's facing, and we've seen this before. We have cameras and the way they're facing, right? So we know that we've just add a vector to the data for this light and say this is the direction we're going. And then we'd also have something like a cutoff angle. So saying that my torch has like a 90-degree cone that it can light things, and outside of that cone it doesn't light anything. So we would add a few bits of data to our point lights if we wanted to turn them into spotlights, to say that if the fragment is inside this cutoff angle, then it gets lit as normal. If the fragment is here outside of the cutoff angle, so we just have to do some calculations on the angle there. Strangely enough, we got dot products for this kind of thing. We can do this quite easily using dot products. Once the fragment goes outside of, so once the dot product for the fragment is lower than the dot product of the cutoff angle, then that fragment doesn't get lit. And we can even do tricky things where when they get close here, we can use a Phong exponent style thing to do a kind of smooth blending on feathering the edge of the torch and stuff like that. So there's a lot of stuff on that. Again, not going to go into huge detail on these things. There's plenty of different techniques that are totally doable once you have a vague understanding of this. And so I'm leaving all of this stuff as things that people might possibly want to look into, but obviously if I'm trying to squeeze in the core and interesting things in each possible topic in the course, then I'm not necessarily going to do a full implementation of spotlights with you. And Bob's asking, is the normal angle range for point lights 0 to 360 degrees? Yeah. So a point light is considered to be radiating in all directions. And if you want to limit it, you'd then use a spotlight. Jason's saying, it's funny how ray tracing solves so many problems while being so simple, whereas you've got to do a whole bunch of heuristics and weird stuff to get this when you're approximating it. Yeah. I mean, like, I liked it when I showed you ray tracing because it was like, yeah, it's just this. I mean, like, it's more than that with a lot of maths behind it and stuff, but it really is just like bounce the light around in straight lines. Like, the understanding how light works is not super complicated. It's just so you got to do it again and again and again. You got to do it billions and billions of times for it to end up looking like the real world. And so the whole graphics field is just jumping through hoops to try to get this stuff to look similar, but even then it's not quite the same. All right, so if we've got these multiple light types, then we might want to put multiple might want to have different effects. So I've got a car in my scene. I want to put spotlights on both its headlights so that it lights up the road in front of it. Or I want to put street lamps, so they're spotlights that aim downwards. I want the sun there. That's a directional light. Or maybe not the sun. I want the moon because I want my other lights to show up. So it's another directional light, you know. I have other lights in my scene, so I don't know what other lights there could be, but you know, just other lights I can make out of point lights and things like that. So how do we process if we've got a lot of different lights in our scene? The frag shader still only runs once per fragment. So we cannot say to the frag shader, you finished with this light, now please run again, but think about this other light in this other position. The frag shader is not going to do that. Once per light. So every fragment has one final frag color. We are not going to be outputting 2 frag colors per fragment. So if we have 2 lights, we need to calculate that all within the one frag shader. And so the process that we might do for these things is we actually do have to run different code for different types of lights. So I only showed you the techniques for point lights. But if you're going to do code for directional lights, you're going to have different code because you're not going to calculate the direction to the light, the L vector. You're going to take the L vector in as an input. And you can't run the same code for both of those. So what you would need to do, the one thing that you can do is you can calculate your ambient light. So you can do this and say, all right, this isn't dependent on the lights. But then you have to loop through all the directional lights in your scene and do the diffuse and specular for them. And then you have to switch to different code, which is your point light code, and you'd loop through all of your point lights and run the diffuse and specular for them. And then you'd loop through all your spotlights and run the diffuse and specular for them. If you've created other types of custom lights, so some of your point lights have attenuation, others don't, you might have a separate loop, or you just might have parts of the code that you run or don't run. One of the downsides to shaders is that every shader, if you have code that you're going to turn on and off, like if point light, else if spotlight, do different code, the downside to doing that is that all possible forks of your if statements are all going to run in all situations, even if the if statement is going one way or the other. You know, when we're doing serial processing in a CPU, we know that our if else statements, some of that code's not going to run. Shaders and our graphics cards are not that simple because they work in lockstep. So in general, we don't put if statements in shaders. Like, I mean, sometimes we might if we're like specifically not rendering something, but we do understand that both sides of that if are going to take up processing time. So sometimes we'll do it, we're just like, no, we'll just run them separately. The downside to this, as you can potentially see, is that heaps of the calculations happening in both of these are identical. So when you get deeper into these kinds of things, instead of just separating the code for these, we might actually bundle certain parts of them together and run something like the calculation of the light direction once, and then use that variable in each 3 of these, right? So we can take things out that are going to be reused. No, that doesn't work. Calculating the light direction doesn't work because they're all different lights. One of the other calculations, there's got to be a different calculation. The direction to the viewer we could do separately and then use that each in all of these, rather than doing the reflect function each time. And as Bob says there, do we just add the effect of all light sources together? Yes. So we add the ambient light to the fragment, we add all the direction lights to the fragment, we add all the point lights to the fragment, and then we add all the spotlights to the fragment. So we're going to be going through and adding them all together. So I'm glad I've timed this right. We've got 6 minutes left. I'm going to talk about an overview of Phong Lighting. So now that you know the entire equation and how to use it, you know a lot of the different possible applications of it, I want to talk about some of the pros and cons of this. So what's good about using Phong Lighting? It computes very fast. It used to be not considered that fast. It used to be like a regular thing, but now if you're only using Phong Lighting, you'd expect our modern graphics cards are going to blitz through this kind of thing, and they're gonna be able to calculate a whole scene of light reasonably quickly. It's a good approximation of real light. I mean, I'm saying that with like a pinch of salt. It's not a good approximation of real light. but it's okay. Like, it's pretty good. You get directional lighting. If you move your lights in the scene, you can tell where the light is by its effect on the scene. You don't even need the light to have its own model. You can kind of tell where the light is based on the scene itself. Like in Warframe that I was playing there, I was like, oh yeah, this light must be here. And I was looking around for the light source. It wasn't even there. It was a virtual entity that the only reason you knew it was there is because you could see it reflecting off things. So that's good. You get directional lighting. You also have a simple model for creating different materials. So if you have the materials on your object and you can alter the balance between the ambient, diffuse, and specular reflectivity of the object, you can get lots of different kinds of surfaces. They're never going to be 100% perfect, but you can see that I can do like shiny plastic, shiny metal, dull plastic. I could do wood. I could do varnished wood, which had a certain amount of specular reflectivity. And each of those is going to have a different balance of settings between diffuse and specular and things like that. And we can do that all via textures and maps on the object itself. I am going to teach you about maps later, but that's next week. I wanted just to do the lighting algorithm this week. We can handle a few different light types as well. And it's a simple enough equation and algorithm that you can modify it easily and get lots of different kind of capabilities in this. So it works in that, you know, I could teach you this entire lighting algorithm in what's been 4 hours of lecturing, and you've probably got a reasonable understanding of it. If I was to say the more advanced lighting techniques like deferred rendering or physically based rendering and stuff like that, it's not going to be that easy. We would need to learn this first before we learn any of those techniques, which is why we're doing this. Okay, so there's a lot good going for it, but there are a lot of issues with it as well. It doesn't always look realistic. Like, you can tell, like, when you look at something that's Phong shaded, especially when someone goes overboard with the specularity, again, going back to Warframe, you can tell it's not real light. You know, it's like, oh, you're really going for it here, aren't you? This isn't a simulation. It also doesn't do very well with sort of mini shadows. Well, it doesn't have any shadows at all, actually. I mean, yes, doesn't do well with shadows. Shadows have to be added in to a system like this because there's nothing in that algorithm that says, hey, is something in the way? Like, if we do this vector to the light, is something in the way? You know, and doing collision detection on that vector in every fragment would get really, really expensive because you have to test every single other triangle in the scene to see if you're going through one of them. Super, super expensive. So we don't even do them that way. And the specular highlights, as I say, can get a little bit realer than real. There are some genuine issues with just the maths. If we do nothing else, there's issues with the maths. So colors can overflow the RGB values. So as I said, if we're just going to loop through all these lights and then just add light to this fragment, how high is this going to get? You know, if I've got a ratio of like 0 to 1.0, if I add like 10 lights to my scene, is my RGB value is going to be like 15 to 20 or something like that, right? I could get really big, and then we would lose our color information because once these things go over 1, they'll usually just get clamped to 1. The other thing that's interesting is these reflected vectors. You know how I was reflecting the light and I was clamping my cos values at 90 degrees? My reflected vector could be an angle that's larger than 90 degrees. It's pretty easy. Like, where is it? Here. All I need to do is lower this light. Oops. Lower this light a little, and this reflected angle here is greater than 90 degrees. If I'm clamping all of my dot products at 0, so anything below 0 is 0, then this is going to do some really, really weird things with that dot product once the reflected vector is actually, it's the dot products here is between the R and the V, but this reflection, if the light source and the camera are near each other and the reflection's going off in that direction or somewhere which is more than 90 degrees from the view vector, it's going to go below 0, which is going to do some really weird things. We may actually, like, if I get time, we may look at solving some of these problems next week. The other issue with this, I think this is one of the most difficult things with Phong Lighting, is it scales based on the number of fragments multiplied by the number of lights. So every fragment in your scene, that's a constant. Every fragment in your scene, you're going to have to work with anyway. But if your amount of processing is now the number of fragments, which is a constant, multiplied by the number of lights, every light you add to your scene adds a whole kind of another screen's worth of processing for your lighting. So instead of this being like a linear amount of work, every time we add lights to our scene, we multiply the amount of work that we're getting. Well, actually, it's kind of linear, but what we're ending up getting is that even though multiple lights should be usable in our scene, what we're getting is a pretty big performance limitation on what we can do based on the number of lights that we have in our scene. There are solutions to all of these problems. So I'm gonna throw some keywords at you, but you don't have to look them up yet. Some of them we'll look into. The overflow of RGB we can handle with things called HDR and bloom and things like that. The reflected vectors, this is an add-on to the Phong shading thing called Blin Phong. We will probably do that, actually, because it's kind of interesting and it's useful, and we're probably going to use that as default. Scaling on fragments by lights is usually handled by this thing called deferred rendering, which I've said that phrase a couple of times, but I doubt that I'm going to have time to explain it in this course, because it requires quite a few more steps to build up the technology before that thing appears. So that's where we're at. Oh, I've gone 2 minutes over. I apologize. But anyway, this is what we covered today. We finished our diffuse and specular, and we looked at different light types, multiple lights, and we looked at some of the pros and cons of Phong lighting. And I've set up a great deal of the issues with Phong lighting that we are going to then cover later. Got some questions here. Actually, you know what I'm going to do? I will officially wrap up the lecture. Then I'll come back and I'll answer the questions that you've got there. Okay. Thank you all. Be back soon. All right, I'm back. We've got some questions here. So Jason's asking, let's say you have a lot of particles like smoke and stuff. Would you clump together the particles and treat them like a mesh with a matte surface and no other shininess specular? Well, that's an interesting thing, Jason. So have a look at smoke, snow, explosion effects, and other things, and particularly compare these in movies to computer games, because you will see something really interesting, that a lot of the time when you have these things called particle effects, like smoke and stuff like that in games, there's no lighting on them. They're removed from the lighting equation, so they exist on their own, and they can appear in the scene. They're put through the shader, but the lighting isn't calculated on them. And they do that because each one of those, like, smoke is made up of, like, hundreds or thousands, depending on how many different little particles. And they're all, like, moving around the scene and stuff. They're all being animated and things. But what we do is we tend to remove a lot of them from the loop, because if we want to light all of them individually, then they just cost a whole lot more. And then we have to work with, like, a lot of transparency stuff, which we do anyway with those things, because they're usually partially transparent. So you just, in a sense, you just remove them from the lighting equation. You don't have to deal with them. And a lot of the time, Clarissa's talking about Genshin and stuff, and doing them 2D. I don't know if you're talking about shadows there or not. We'll talk about what you're talking about in a second, Clarissa. But yeah, a lot of particle effects, what they will do is, like, they will make them as if the particles themselves are sort of giving off their own light. So when you see an explosion that has fire and smoke in it, the smoke will be lit by its own fire. But an explosion with smoke and fire that happens in a scene that has, like, say, green neon lighting and stuff, you check that out. Some games will and some games won't. Plenty of games, that smoke and fire will have no green in it. It will not be taking any lighting from the scene, but it'll have plenty of orange from its own explosion. So you can see how it's been made pre-baked in a sense with its own lighting. But it won't necessarily be able to take part in the lighting from the scene because that ends up being too expensive. So you'll get this back and forth like that. So with a lot of like those particles, you can't really treat them as a surface to be lit. You'd have to do them as different little pieces. And then what you need is for some of them to be obscuring each other to a sense where some of them absorbs the light. So if there was that kind of green neon light next to an explosion, you need that green neon light to be filtering through the smoke and lighting the edges more, but like attenuating as it goes through. It's not really attenuated, it's being obscured by lots of tiny particles. That's expensive to do. You will definitely see that in films. So you'll see explosions in films will be lit by environmental lights and things like that. In games, less so. But some games you will see it. I'm thinking of maybe, I might need to reinstall it, having a closer look at Cyberpunk. Because it's probably one of the most advanced lighting engines that is in games at the moment. It's got a lot of full-on reflections. You can turn on the ray tracing and see how that looks and stuff. So maybe I have to reinstall Cyberpunk. I said I wouldn't. Maybe I can find a different game that uses all the RTX stuff instead. Yeah, so it's that kind of thing. Yeah, so Jason, like a lot of particles. What we do to make particles is like there's a lot of these tiny little rectangles, and then the particle is an alpha blended thing on that, or even a cutout stencil on that. So particle effects, when you can see the multiple little objects, are often like that. I'm thinking snow and stuff like that, where you see the individual pieces of snow kind of moving across your screen. Each one of those is like a little rectangle that's just sliding across your screen, and the texture on it might be an animated texture. So it's cycling through texture coordinates like a sprite sheet, so that it doesn't stay as the same shape. It just kind of shimmers and looks like it's rotating, but it's actually just the image that's rotating. A lot of snow and like falling leaves and stuff like that is that, where it doesn't have the geometry you think it does. It's actually just a hand-drawn animation that's on a flat thing that moves past your vision. As Clarissa's saying with like a lot of the Genshin particles, totally. They're 2D things that are actually 2D animated by someone drawing them. And they never turn like they look like they're doing. Like there's these maple leaves that flutter. They're not fluttering. They're just a rectangle that's moving like that, and a drawing of something fluttering on the rectangle. There was a time during the planning for this course where I had particle systems in, but it's not, it's like a side topic. It wasn't core enough for me to leave it in the course, unfortunately. I will mention it. I mean, I've actually kind of already taught you how to do them in a sense, just in side conversations we had. But I don't think I really have time to devote like half of a lecture or something to how they work. But maybe we'll see, because we actually got through the lighting stuff, the Phong shading, a little bit quicker than I'd planned. I'm hoping that doesn't mean that I've covered it in a way that people won't understand the details, but hopefully it's fine. So there may be a little bit of a lecture free somewhere to add in some things, but we'll see. I'm just trying to squeeze in as much as I can at the end of the course, knowing that a lot of the stuff that I'm talking about at the end of the course is not necessarily stuff that you need to know. It's just all these expansions and stuff. So we've now gotten through geometry and lighting. So we actually have the core now of what is modern graphics. But a lot of what you see in games is way more complicated than what we've shown. So we're still in the late 90s at the moment. We've gotten past the early 90s. So when I was talking about Quake, Quake had no lighting. Quake, I mean, I don't want to say it has no lighting, but it only had pre-baked lighting. So that is these things called light maps, where when you don't have the time to render the light, I should talk about these in a lecture, but I'll just give you a preview. If you don't have the time to render the light in a scene, you could render the light onto the idea of the scene, and then bake the lighting into the textures, and then put textures of the floor with these like like shadows on it from windows and stuff like that. But you're not even calculating the light coming through the windows because you knew that the directional light was always going to be in the same position. The windows were always going to be in the same position. So you just bake it into the floor. And you go, the floor's texture has these bright bits and these dark bits. And then you get away with it because the only thing you're doing then is just sampling a texture. You're not doing the lighting. And you don't notice there's an issue until you like walk between where these things are happening and then it doesn't have any effect on it. Because if you never move the light source, you never have to change where the shadows are. So that's like the earliest kind of... Well, not actually the earliest shadows. The earliest shadows is the circle underneath the character. It's just like a grey circle underneath the character. That would be like the earliest shadows. Yeah, so Clarissa was asking, will we learn how to do lighting when there are objects in the way? No. Maybe. It's funny, right? Because the objects in the way thing requires us to figure out if something's in the way and then deny lighting to certain fragments. There are techniques to do this. It is on the list of possible topics that we can do. And that's this thing called shadow mapping. We might do it. We'll see. I think that I have time now. I think that I have time in the lectures to do it, but not 100% sure on that. Yeah. So actually, Simon's already said that. The buzzword is called shadow mapping. Might mention them in our tute at some point. Yeah. So there is a technique that we can use. It just depends. Like, you know, when we've got, what are we, week 7? Week 7 and 8's tutorials are all lighting stuff. We're going to do more stuff on lighting. This isn't the end of lighting. There's way more cool stuff that we can do with it. So we're still going to be doing lighting stuff next week. The week after, I want to do some stuff with reflections and things. Reflections and shadow mapping are similar techniques, but we're not going to cover them both in one week. That would be painful, right? Or maybe we could. I don't know. Yeah, we'll see how we go. You can see how, like, I'm still reacting to how much we can get through in this course, because this is kind of, it's not a first offering of this course, but for me it's a first offering of this course, so I'm still trying things. Simon's like, there are no shadows in Tune 8. We can't. It's too late. Don't do this to me. Because I think Simon's already been working on the tutorial for week 9, which I'm pretty sure is all reflections, not shadow mapping, which is cool because reflections are really cool. Yeah. Yeah. So Jason's like, yeah, pre-making particles as texture animations on transparent little objects. Yeah. So what we can do with stuff like that is we can do a lot of, because as you can see, lighting can be very expensive. So if we can do things in advance and bake them into textures, then we don't need as much lighting. Like old games, early eras of stuff like World of Warcraft and things were very, very much based on accessibility for hardware. So they were expecting that a lot of people had, you know, just pretty budget hardware on their computers. So what they did was they said, all right, what's the most expensive thing? Geometry and lighting. What's the cheapest thing? Sampling textures. So what we'll do is we'll put all this work into high quality textures, and the polygons, that they were so low, the number of polygons in World of Warcraft. Like, you'd look at it and this tree would just be like, nyeh, nyeh, nyeh. Like, you could just look and see the verts and the edges. But that tree had this beautifully painted texture winding up it, and you're just like, okay, I'm good. I believe that, you know? And it's a cartoony world anyway. You don't need realism in Warcraft. I mean, you've got like these minotaurs running around throwing moonbeams at people, right? Like, we've left reality so far behind at that point, so you don't need like fully realistic lighting. So early on had very rudimentary lighting. I mean, the game has been going for like 14 years, I want to say. I don't know. I'm like a recovering addict in a sense. Like, I got off World of Warcraft about 4 or 5 years ago, and I can't go back anymore. It's like if you used to smoke and people start smoking around you, it's like, you know, like it's worse than if you'd never smoked. That's me as well. So it's a similar thing. I must have some kind of addictive personality. I shouldn't be in computer games. Anyway, I play Genshin now. Yeah, so we get this kind of thing where there are parts of this particular rendering pipeline that are easier to run than others. So putting a lot of information into textures and just sampling them. Sampling the texture is the same cost if it's a completely flat one color texture than if it is like a super, super complicated multiple like colors and all these kind of gradations and a whole lot of effort texture. Our processor in real time, our GPU in real time is doing the same amount of work regardless of the quality of the texture, which is why so much stuff gets put into textures. But, you know, we're in a moving field here where the hardware keeps getting better. And at the moment, I guess the one good side to everyone taking our graphics cards for Bitcoin mining is that that's pumping a lot of money into Nvidia and ATI. So maybe because every single graphics card they make is already accounted for in sales before it even leaves the factory, maybe there's a lot more money flowing into those companies, and the flow-on effect from this in the next few years is that the graphics hardware is going to be more efficient and working better, and we're going to be able to use it to do more cool stuff. I hope. Don't know. I'm just a bit like, yeah. I'm a bit cynical about the whole Bitcoin thing. As someone who loves graphics cards for a completely different reason, I can't not be cynical about Bitcoin mining. I mean, it's just regardless of all the moral quandaries of Bitcoin mining in general. Yeah. So, yeah, there's a lot of cool stuff going on where seeing which things cost the most in the pipeline, and then you'll see where the technology pushes to try to do different things. Jason's asking if the GPU can offload some of the stuff to the CPU for the graphics pipeline if you've got something like a GPU bottlenecked game. Yes and no. Technically, all of the maths that the GPU is doing can be done on the CPU. The only problem is like the bus to move data back and forth the GPU from the CPU to the GPU is so slow in comparison to the performance capability of both of those objects that waiting for the data transfer is going to cost you more a lot of the time than just doing it yourself. You lose your kind of memory locality as well by passing some of it to the CPU and then needing it back. It's like if everything is organized in your GPU RAM, it's quicker to just kind of do it in there. So in general, the only things that we would pass to the CPU are calculations of positions for animations, because that's a slower kind of thing. Like it's not, it does happen every frame, but it's information that can get passed into the GPU every frame, and it's kind of okay. So we will do animations, physics, other things like AI, I guess, like game AI and stuff like that will be done on the CPU. Even physics isn't always done on the CPU. Like Nvidia had a huge push, I don't know when, a decade ago or something, to do with this thing called PhysX, which was like, hey, we can use the graphics card's amazing, you know, floating point calculation system and ability to deal with so many objects at once to do the physics. So they started doing stuff like cloth physics and particle physics and stuff on the graphics card. So even that's not even getting offloaded to the CPU. You will find that in the majority of games, especially high-end games nowadays, that they are all GPU bottlenecked. You can run your stats. Like you've seen, like I do this because I like to know what's going on. You can actually see here in the top left corner here, I've got my GPU and CPU stats. I've got my frame rate. I've got my temperatures as well. I get into overclocking and stuff because it's just fun. It's just a hobby thing. Although I tend to only overclock my computer once it starts not performing as well in things. Because, you know, I don't just want to burn out my components the second I buy them. A lot of the time I let my computer run for a year or two, and then I'm just like, I could buy a new computer, or I could tweak the crap out of this one and make it perform better. And then if it burns out and dies, then I was already thinking about buying a new computer, so it's okay. Don't necessarily want to burn out a brand new machine. But I do like watching the stats, and I do like seeing the balance. And what I've seen most of the time is that your GPU is just redlining at 100% while your CPU is sitting there at 50% utilization. And there's not much the CPU can do to help your GPU in those situations, because usually the reason for that is you've turned up all of your settings up really high because you want your really nice reflections, you want your really nice like anti-aliasing, and you want your really high resolution and stuff. You know, you're running at 4K, you're gonna be like you're gonna be like using your graphics card a lot. I prefer games at 1440p, which is like the one level down, because it's like, what is it? It's literally half or even a third of the pixels, because of the multiplier between them. So you know your graphics card's doing much less work, but you can, but you kinda can't always see the difference between them. So, you know, if you don't use a huge monitor, you don't use a huge 4K monitor, you're going to give your graphics card a break, which is the number of fragments that they're going to have to render. And then you can get high quality image with less pixels. So it's a decision that has to be made, I guess. I mean, I would even consider running a 1080p at really, really high settings, but I've got a good enough rig that I can run 1440p at about 100 FPS in most things. What's my Warframe there? I'm looking at it. That thing's running at 142 in that, so I think that's capped. So that's going full. Yeah, because it was only using 50% of my GPU in that particular scene. I think when more people are running around, you're in combat, there's special effects happening, it's going to drop a little. But Warframe's an older engine, so I'd expect my computer to run that 144 hertz. Yeah, Simon's talking about the difference between CPU and GPU stuff there in chat. It's also quite funny when you talk about offloading work to the CPU, it actually goes in the other direction more often, where work that used to be done on the CPU is now being run on GPUs. Anything that involves multiple floating point multiplications is happening on GPUs a lot. So, as I said, Bitcoin mining, but also like more kind of real world use things, like deep learning and stuff like that running on GPUs. So it's pretty cool. Simon's running 1080p at 240 hertz. That's a pretty specialized monitor. 1080p 480 hertz monitors. Yeah, that is upgrade for virtual desktop switching. For me, there's a few things that I like. I like to have visual fidelity in what I'm doing, because this is for games, because I know too much about it. I know too much about graphics to see when certain things aren't running. So it's like, you know, when ambient occlusion's not running in a game, I'm just like, ugh, all of your corners are ugly, you know? So anytime there's like a crevice in between things and it doesn't have a little bit of shading around it, like I get annoyed, right? So there's all those little things I want to be able to turn them on, because I know that we have the capability for it. So if I do want to turn them on, I know that everything that I turn on for quality is going to drop my frame rate. So I got to keep my pixel count down so that my frame rate and my animations are smooth, and I like it about 100 frames. I do play games lower than 100 frames. When it gets down to about 80, I'm still okay with that. But if it gets below 60, I'm just like, I don't like this, you know? And so I want my cake and I want to eat it too. So I want my 100 frames and I want my quality effects as well. So, you know, I have no choice. If I'm going to do that, then I'm spending thousands of dollars on my hardware. It's just the way it goes. But, you know, at least this year, this computer, I can now do this computer as a tax write-off, because I am unable to teach graphics without having played these games and be able to bring up these games and go, okay, you can see that in this is happening. And the only reason I know which games to bring up is I've played a whole variety of them. I don't know if I'm going to get away with tax deducting my entire Steam library and like all of the whaling for characters in Genshin. I don't think that that's a viable thing to do, but some of it definitely. Every game that I've used in this course, I will try at least to tax deduct some of it. I might have to talk to an accountant to see whether I could actually be allowed to do this, but you know, yeah. Yeah, and as Simon's saying that once you exceed 60 hertz, you can't go back. I mean, there was this dark ages of graphics where the monitors took us back to 60 hertz and kept us there for like 2 decades, I think. When we went from CRT monitors to LCD panels, and they were like, no, we can't go above 60. And we were just like, what? All the games we were playing at 100 hertz before that. Like Quake 3, we were like, go at 100 frames. You know, you can go at 100 frames to do it. And then we got brought back by the LCDs, and we had to just kind of train ourselves to accept 60 hertz until quite recently. Only in the last sort of 5 years or so, we went up to 120 and then 144, and now we're back in this realm where, like, if we're around 100 hertz, like, it's hard to tell the difference between 100 and 144. So I'm just like, okay, that's where I'm comfortable. But anything below 100, I'm just like, I'm noticing that something's up. So I kind of like it at that level. So I'm glad that our hardware technology has brought us back to the point where we can get to the frame rates where we can trick ourselves into completely not noticing frame rate. And it's really weird because, like, you know, when you go see movies and Hollywood's still on like 24 frames a second, and you're like, whoa, they need so much motion blur to cover that. I saw Spider-Man at IMAX, like one of the old Spider-Man movies way, way back in the day. And it was like still images of Spider-Man swinging across the screen. And because you're at IMAX, these images were like 10 meters apart. And you were just like, oh my god, I can't see anything. Why is your frame rate so low? You know? So it's quite funny. Simon's like, controversial stance, games are more than just good graphics. No, I mean, that's totally true. If this was a games course and not a graphics course, I would not be talking about, like, you know, what we need for graphics. Or maybe there'd be one lecture on the spectacle of high quality graphics, but the rest of it would all be about, like, the only reason games work is good design. And you can go back, like, notice how excited people are at the moment that the Nintendo online accounts have just brought back a whole bunch of N64 games. That just goes to show that design is more important than graphics. I mean, to a certain point, you go back far enough in time and you need better graphics. Like, I grew up with an Atari 2600 and I'm just like, yeah, you know what? I'm never going back to those graphics. Like, I will go back to certain eras. Like, I go back to, like, Sega Mega Drive, Super Nintendo eras and stuff like that. Like, Street Fighter, I love it because there's certain charm in well-painted sprites, even at lower resolutions and things like that. Or even remastering of those games where they just up the resolution. But beyond a certain point, I'm just like, I'm not interested. And then some games I'll play just to see how cool the effects are. It's like, what cool stuff have you done with graphics? So I've been looking around and seeing what games are making the best use of ray tracing and stuff. I picked up this game called Control. I haven't played it yet, but apparently it's very good use of new RTX hardware. So maybe I'll show that in one of the later lectures because I haven't actually installed it or played it yet or anything. Yeah, Sam's like, your parents said, why are you playing Minecraft? It has bad graphics. But I mean, you know, Minecraft has never been about the graphics, and also it has escaped needing to update itself as much because it was never about the graphics. And that's a beautiful thing. If you're not about the graphics, then you're not stuck on a technology curve. You're not dating yourself by your technology curve because you were never part of that race. So you can't lose a race that you're not taking part in a sense. And that's one of the beauties of Minecraft. Except when they did ray tracing in Minecraft, I'm just like, okay, I don't see why that's necessary, but, like, I'm glad that you're experimenting with the new tech. That's kind of cool. I have a feeling that that's because Minecraft is owned by Microsoft. Microsoft developed DirectX. DirectX was the first renderer to hook in with NVIDIA ray tracing, so they were like, well, let's throw it into the biggest game that we own and see how it goes. You know, I assume that Halo Infinite will have ray tracing as well, but I haven't really looked into it. That's one of the other big Microsoft titles. Jason's like, no, people love graphical fidelity. We do. We do. Some games just look pretty. Like Warframe is one of those games where it just looks so good. It's not just the still images of it. The animation in the game is top notch. Everything is smooth, and like you get these robots that look like this kind of like they look like that kind of big dog movement in the robots. They even got the same kind of legs, I think. And then the human and organic animations got all this like kind of seaweeding and stuff going. It looks really good in motion. Warframe, I think, is like one of the most graphically accomplished games of its time, because everything looks and feels smooth. Everything looks and feels right as well. I mean, like, it's a little bit overblown. Everything's just like, whoa, it's so shiny, but it's still kind of cool. I still like it. I think it's one of the best put together graphics engines. Not just graphics, but all of the art that leads into it. All of this kind of bio-organic, biotechnological, organic kind of melding that has come across really, really well. Jason's like 40% graphics, 40% gameplay, 10% plot, and 10% franchise value. Yeah. Yeah, and Sam, like, Nintendo has been able to escape the graphics race in a sense. So they're not in the race, but they're still winning on their artistic value. You look at Breath of the Wild, it's beautiful. And it's like on release, the Switch was still running a mobile processor at the time, you know. It was hardly a serious kind of graphics processing unit. Like, and the thing can still run for like hours on batteries, you know. Like, try running an NVIDIA 3090 for any amount of time on batteries on a laptop. It's not going to work, right? It's gonna burn out in an hour or something. So there's some beauty in being able to do your design well enough that it really does look great. It looks great because of use of color and things like that. It doesn't have to be high-end lighting equations that makes something look good. So basically, everything I'm teaching this course is worthless. It's true though. It's true though. It's worth it for particular things. But for other things, it's not necessary. You know. So, again, it's this constant kind of struggle in computer graphics and in games between what looks good and what is an accurate simulation of real-world lighting. The accurate simulation requires a great deal of computational capability, but there's plenty of games that look great without using it, you know? So there's different things. But also, what looks good, what looks great, what I like looking at, it's subjective, you know? And so it's about hooking into a lot of people's subjective tastes. And if you hook into only very few people's subjective tastes, that doesn't make you less interesting as a game or as a graphical application. If you can tug the heartstrings of a small number of people, you still tugged heartstrings with that, you know? So it's not necessarily that, like, you have to be the most popular thing. Not everything has to be Grand Theft Auto, you know? Like, there's something about that game, though, that just somehow can grab a very, very wide audience. But other games don't have as wide an audience, but they don't need it, you know? They can have their artistic expression without needing that. Jason saying, yeah, Nintendo with their proprietary hardware, software, full stack is kind of amazing. Yeah. Yeah, you're saying the same thing I was saying, right? You can put together Breath of the Wild on a brick that's like 20% of the PlayStation 4's performance. The PlayStation 4 has even already been superseded, and the Switch is just still happily chugging away, and people are still buying it because it's not necessarily the raw computational power of a gaming console that makes it worth playing. And it's like, would you agree that Nintendo is the gold standard for video games? Yeah, I don't think there's a gold standard anywhere else, because the way that I would judge video games, and this is like stepping outside of the graphics lecture, and into like I haven't done any games teaching it at CSC, but like I used to teach people how to make games. The gold standard on computer games is the effect they have on the people who are playing them. Nothing else is as important, right? The whole point, the reason why we buy computer games is so that they will have an effect on us. We're here to be entertained. You know, we're specifically wanting entertainment from these things. If you get entertainment from it, then it has succeeded. So that is the measure that it should be. So whether it has very, very good graphics or not, it's not hugely important. Whether it has bad graphics is maybe important, because the worse it is, the more it removes you from the immersion, which can affect your entertainment, you know. But a lot of the time, it's a fantasy world. It doesn't have to be real. We can have it any way we want, in a sense. Yeah. Sam saying Metroid Dread is the gold standard, so I assume you've just gotten it recently and you're loving it. Have you heard of break time? I would love it if we could actually implement break time, but I'm feeling that like it felt too AAA to me. It did not feel like a little indie that you'd be able to put together with a bunch of people. Anyway, speaking of break time, I have now hung around for ages beyond the end of the lecture, but it's fun. It's fun talking about, you know, the bigger picture, I think, in games and graphics. And I think it's important to have these things, because if you don't have this bigger picture, you don't have the context for what you're making, you don't have a reason to want to care about these little curves and this lighting and stuff like that. The reason you want to care about these things is what you want to create with it, you know? So I think it's quite important. But having said that, I gotta go have some lunch and stuff. All right. Thank you all. I'm gonna wrap it up here. See you next week. Next week, we're gonna go into like a lot of these things. Like, this stuff is not perfect. It does not work perfectly. We need to actually look at some of these things and look at some of the ways we might fix these things, or even like, how do we get these things to look more like, how do we use these things to actually push them further than what I've shown you, because what I've shown you is only like super basic stuff. So we're gonna add on stuff to our lighting and our materials and stuff like that. All right, see you all next week. Hopefully everyone can get some cool lighting going in your tutorials as well. Bye.